This is part 2 of a series of tutorials looking at using the program Scatter for analysing solution X-ray scattering data, specifically biological scattering data. And in this tutorial I'm going to talk about using Scatter to reduce SAXS data that you got from coupled size exclusion chromatography experiments. That is a common thing on beamlines, SAXS beamlines nowadays, to have a HPLC system with a sizing column attached to it, and then the output from the sizing column goes straight through your SAXS beamline, and you collect a whole series of SAXS images of the output from the column, and then you want to reduce that to get at your data. Okay, so here is Scatter. In the last tutorial I showed you how to set Scatter up to download and launch it. So if you aren't at this step, go back a step and look at the other tutorial. And then I have a directory in which I have a whole series of SAXS images. These are radially integrated images, .dat. They're basically text files. They have 3 columns: Q, which is the scattering angle vector, I, which is the intensity, and then E, which is the error column. So they're just simple text files. So we have a whole series of them here, from 1 to 591, so almost 600 images. We want to have a look at these, which ones have the protein sample in, which ones are buffer background, and how can we get at our data. Okay, so what I'm going to do is I've selected image number 1. I scroll down to the bottom, I'm going to hold shift and select the whole block. I'm going to go back to the top and I'm going to grab image number 1 as a handle, and I'm going to drag that into the samples field inside this subtract tab in Scatter. Okay, so I'm going to do that. What you'll see is that the scroll bar here starts to come across, and it's going to take a little while for Scatter to load 600 images. So we can wait for that. One thing to point out while we're waiting: depending on your operating system, sometimes you'll select a whole block of images like that, and you'll grab one to use as a handle. Let's say I just grabbed image 15 here and dragged those over. Some operating systems will then put image 15 at the top, and then it will go down to image 591, and then at the end of that you'll have images 1 to 14 tagged on the end. And what that means is when you come to look at your trace, it'll be discontinuous. There'll be a sort of things are out of order. So just be careful that you drag things in order. Okay. Now what we're actually doing is really following the instructions to some degree in this little tab here. So it says drag frames in order. This in order refers to that common mistake of dragging them out of order. Drag your frames in order to the samples on the left. Wait. Okay, and then click trace. So I'm just going to do that. Now, what trace does, the first thing we want to know really is where is our buffer and where is our sample. Okay, this is a trace. This looks a little bit funny actually, it's just the way it's been run. There's a little bit of a dip here. Something funny went on with the column. Usually this is just a flat line. It doesn't really matter. The fact is we're trying to find where our sample is. So the trace button will analyze all 591 images, looking for the images with the least amount of scattering information in them, and it's going to automatically set those as the blank. That is a useful first approximation that gives you a trace that is interpretable, but it's not by any means the sort of definitive buffer blank. Okay, so the first thing you want to do is choose where your buffer blank is. Now you can see there's a nice flat piece of buffer here. There's a bit of an anomaly. We don't want to choose this. And then we've also got some buffer at the end. So the rule of thumb is move far enough away from your peak that you're not going to be picking up some of the scattering particles in your buffer blank, but you also want to be reasonably close to your peak so that the buffer is a good match. Okay, so if it was me, I would probably select a little window here Okay, so I've done that, selected a window. What that's done is in your tab here, it's just put some tick marks next to the images that correspond to that window that we selected. You can see I've selected, I don't know, maybe 20 or 30 images, okay? And then I say set buffer, okay? And that just copies these images over into the buffer background tab, okay? Now, that's fine. I could leave it there, and I think I will. You can continue to select. So if I might select something else, and if I was to go set buffer, that would copy these in addition to those. So you could have multiple regions that you're choosing as a buffer, or you could just do one. Okay. Now, the next thing it says, is we really want to look at this peak more closely. We want to zoom in and we want to see how the scattering pattern changes across the peak, okay? And there's no way of zooming in the signal plot window. So what to do next is choose the peak area, and inside scatter you say set range, okay? And you can see it's set the range here, okay? So next time when we want to look at the trace, I'm going to use this signal plot button, and then it's just going to zoom in on this range, and we're not going to see the whole thing. So that's just quite a useful thing to do, okay? The other thing we want to look at is how the radius of gyration, which is a sort of a good descriptor of what the scattering data looks like. How does the radius of gyration vary across this peak, okay? And to do that, we're going to, for each of these images, calculate RG and then plot that onto the plot. To get RG on the plot, we choose this Add RG to Signal Plot tab, okay? Now, if we were calculating RG for this plot here, we don't want to try calculating an RG for every single image where it's clearly just buffer blank. And so the way that we exclude these from the RG calculation is we set a threshold, okay? And you can see the buffer background is round about 0.44 on this y-axis. I'm going to say only calculate an RG for things above 0.46, okay? So I can close that now, and I'm going to set the threshold to 0.46. This won't always be 0.46. It's a good idea to choose an appropriate value to give you the radius of gyration for the section that you want, okay? And then I'm going to do signal plot, okay? And again, it's going to take a little while. We're going through each of those images, and we're calculating our radius of gyration for each one. Okay, so it's finished, and here's the plot. Okay, so this is really useful. This curve here is actually BSA. Looks a bit funny. This peak is fairly asymmetric, and there's some other things coming in here as well. You can see that the radius of gyration across the peak is largely flat. It's perhaps sloping up slightly, which is a bit odd. But then at the leading edge of the peak, we start getting larger molecular weight material, with high RG values, and then it goes off to, something very large as we look at some of this stuff out here, okay? So what we want to do now is choose the part of this curve that we are interested in. Now, I would tend to avoid this stuff up here, but you could choose part of the middle of the peak there, like that, okay? And again, all that's done is it's selected in the samples tab. It's just selected these ones here, okay? Now, we can output this. So let's call this, BSA peak, or monomer would be a good name for that. It's going to average together the files that we've chosen using this SVD statistical approach. Set output directory. I'm just going to write it out into my SECS folder here, but you can choose whichever folder you want. Okay, and then we go subtract using the selected buffers. It's going to have a think. It's averaging the buffers. It's averaging the selected samples, and it's outputting the final thing. So it automatically opens them in files, and they're in here. You can see those. it outputs two files. One is an average and the other is a median. Hopefully those two are identical, and you can see here they really superimpose. What that's telling you is that there weren't outliers in that averaging window. If the median and the average look different, it means that there were some outliers that weren't included in the median calculation but were in the average calculation. And the thing to do in that case is to go back and have a look more closely at what you ended up averaging. And one way of doing that is you could uncheck these options here, and then when you do subtract again, it'll output each file that you selected as a separate thing, and then you can have a look through them and hopefully you'll see that one is an outlier or there's a couple of outliers, and you can reject them and then average them again. But hopefully these are looking good. Okay, and so now we can go ahead and analyze these further, look at the data quality, etc., etc. You can let me just bring back up the signal plot. So obviously we chose a little window there in that monomer peak. We're calling this the monomer peak. There was also a little peak here, let's call this the dimer peak, and you can see it's kind of sloping, the RG is kind of sloping down here, but this, you could almost convince yourself that this is a little plateau region here. So I could choose this as well, call this dimer, and I'll put the averaging back on, subtract, and that'll output the dimer peak as well. And you could go on. We chose this region as the monomer here. We might think, is this lower than this? Let's choose this as well. We can output this as BSA monomer part 2 or what have you. So you can choose multiple regions across the peak and have a look at them. Okay, and again, these have been opened up in files. You can see the signal's weaker here, but the fact that this is kind of lower down, looks a bit funny, but anyway, that corresponds to that larger peak. Okay, so that's how to go about looking at size exclusion SAXS data using scatter.